Hello everyone, this is Radha presenting my findings for Physics Lab 2, which was on projectile motion. The lab investigated projectile motion by combining experimental analysis with computational modeling. First, I used Tracker to extract position and time data from a recorded video of a projectile. Then, I built a physics-based model in CloseScript using Newton's second law. Finally, I compared the real trajectory to both a gravity-only model and a gravity plus drag model. The purpose of this lab was to analyze projectile motion using real data and test how well physics principles predict motion. Specifically, I used Tracker to determine the initial position, time, and velocity, and then implemented them into a computational model to match reality as close as possible. So in class, as you can see on the video, we used a marker to record the projectile motion, and then we measured its mass, which came to 6.35 gram, and a ruler was kept in frame for calibration. In the tracker, I first imported the video of the projectile motion. I calibrated the scale using the known length in the video so that the pixel measurements converted to meters. Then I aligned the coordinate axis so that x was horizontal and y was vertical. And then I extracted the initial time, which, as you can see from the picture, there were quite a lot of data. So we used the first instance of time data that was available, which is the zoomed in picture. So as you can see, it does not start from time 0, but rather at 0.285 seconds. And so I set t is equal to 0.25 in CloseScript 2 so that the computational model starts at the same exact moment as the experimental data for alignment. For extracting the initial position and initial velocity, I again used the coordinates which you can see in the zoomed in picture. So the initial x was 0.707 and then the y coordinate was 0.0773, which I put into my code. And for the velocity, Tracker automatically calculates it by calculating the slope. So I just clicked on that and got my readings from there actually. The fundamental physics principle that was used was Newton's second law, which says that F is equal to ma. In this code, I calculated the net force and then divided by mass to obtain acceleration. Then I updated velocity and position using Euler's method, as you can see below. Then we have our main results. The main goal of the results section was to determine how well the computational model matched the experimental portion and whether, including drag, improved the agreement. So in this video that you can see, it is from the graph of no drag, and you can also see the graph. That's just one of the trajectories. We compared it with the Tracker experimental data and also the one with drag. So how did we choose the drag? I accounted for drag via the following formula. Here, the if-else block ensures that when the speed is 0, the drag force is also 0. This prevents division errors when calculating the unit velocity vector. When the object is moving, the drag force is calculated as negative b times speed squared times the unit vector of velocity. This means that the drag force always points opposite to the direction of motion and increases with speed squared. Also, the value of the drag was not chosen arbitrarily. We used b is equal to 0.0015. So when we used b is equal to 0, there was no air resistance, and the simulated trajectory overshot the experimental data, so it traveled farther horizontally and stayed higher longer. So then I gradually increased the drag constant and then reran the model until it got too high, so then it would drop too quickly. So through trial and comparison, b is equal to 0.0015 produced the closest alignment between the CloseScript trajectory and the Tracker trajectory. Finally, I took all the data from the Tracker and both of the CloseScript models. I used the Tracker data as the base because there were less values in Tracker, and then I found the y coordinates for those same x coordinates and time that were in the Tracker, and then I tabulated them in Excel. So over here, you can see that we have 4 columns. So column 1 has the x values, which is the common horizontal position for all of them. And then column 2 has the y values from the Tracker. And then column 3 has y values from CloseScript with no drag. And then the 4th column has the y values from CloseScript with drag. One thing to note that I aligned both data sets so that they correspond to the same time interval. So they all started at time is equal to 0.285 seconds. And here is our main graph, where you can see all 3 graphs together. The gravity-only model produces a perfect parabola that travels further and stays higher than the experimental data. The drag model shifts downward and shortens the range. The drag model closely overlaps the Tracker data, especially in the later portion of motion. This suggests that air resistance is present and that including a quadratic drag term improves the accuracy of the model. However, we did make some assumptions, which is that the motion is 2D, there is no spin, we have a constant force of gravitational acceleration, drag is proportional to v squared, and the camera calibration is accurate. However, there could have been the following error. The manual tracking introduces small human error. Calibration errors affect scaling. The Euler integration method introduces small numerical errors, though using a small timestamp reduces this. So we had some special questions that we also had to answer, which is that what would be the effect of terminal velocity. So as we know, terminal velocity happens when F net is equal to 0. So for an object that is falling with drag at terminal velocity, the weight will equal to drag, so the acceleration becomes 0. So naturally, in the model where there was no drag, acceleration was constant, the slope is constant, and the velocity keeps becoming more negative. So it does not produce terminal velocity. As you can see, by the way, these graphs were directly just taken straight out from CloseScript. For the drag model, the acceleration is decreasing, the drag force is increasing, and the net force is decreasing. However, it does not flatten out because the experiment does not go long enough for it to reach terminal velocity, which is because the drag force hasn't yet equaled the force of gravity. Okay, so what similar experiment could we design to ensure that we do see terminal velocity? So we would need an experiment where the object falls long enough, the drag force becomes comparable to weight, and the object must be small and heavy related to drag. So a better experiment would probably be to drop maybe a coffee filter or a lightweight paper cone or a ping pong ball from a large height. Because these objects have large surface area, small mass, and strong drag effects, the velocity versus time graph would increase at first and then flatten into a horizontal line. That flat region would be our terminal velocity, and we would be able to read it off directly from the graph. Now, what if it was thrown straight up instead? So in the original experiment, the projectile was launched at an angle. So our the time taken to peak and the time taken to fall, it only is determined by the vertical component of the velocity. So which, as you can see, if we use which was 1.6, the vertical component, which when we used, our time taken was 0.16 seconds. So if the it was thrown up with the same initial speed magnitude, we would first have to calculate the speed magnitude that was originally there. So we combine the x components and the y components, and we received speed is equal to 3.14 meters per second. Then our time up in the air would be 0.32 seconds. So a straight up throw has about double the upward time. This does not necessarily need to be double. In this particular case, it is just double. So in general, it would just be higher. So it reaches the higher maximum height, and then it takes longer to hit the ground. Finally, the gravity-only model did not fully match the experimental trajectory. After incorporating a quadratic drag term and adjusting the drag constant to 0.0015, the simulation aligned much more closely with the trigger data. This indicates that air resistance plays a measurable role in the motion and validates the computational modeling approach. Thank you!